on over the past, I would say, maybe 5 to 8 years. Yeah, so actually I'm speaking now from Germany, but the place where I live in is Tallinn, which is not far from you, just on the other side of the Baltic Sea. So you could, when you look at the east, you see Tallinn, I guess, yeah. So, and this is what is going on in electrochemical impedance spectroscopy over the past 25 years. I just collected this data from Scopus website. This is a huge scientific database from Elsevier, as you know. So this is number of publication on a broader topic, just in general electrochemical impedance spectroscopy per year. And as you could see, we have nearly 4,000 papers per year nowadays. Okay, in year 2000, we have 300 to 400. So this is a really enormous growth. And the interest in this technique is because it's really very attractive. It is relatively simple, but most important that it's non-invasive, non-destructive, and you could test fuel cells in operandi, just in run. You can make this test and characterization of fuel cells when they run. So which is really tremendous advantage of this technique. So I presume that not everyone is familiar with idea of impedance. So let me just give you a mechanical equivalent just to explain what it is all about. So suppose that you have a box with two masses hanging on springs inside. The box is closed, the masses are different, and your problem is to measure M small and M large. Of course, you could weight the box, and this gives you sum of these masses, M plus M, but not separate, okay? What you could do, okay, you could start shaking this box, and at some frequencies you would hear, you would feel the tremendous resonance. These masses would start hitting the box floor, and you could measure these frequencies. This would be omega M small and omega M large. And once you have a physical model for this process, you know equation. So this frequency is square root of spring, what is property, K divided by mass, okay? So now you can make a ratio of these frequencies. It gives you a ratio of a square of the ratio of this frequency gives you a ratio of these masses. You can solve these two equations and find M large and M small. So this is really the idea of impedance. Of course, we do not shake fuel cells. Rather we excite them using a small amplitude perturbation of potential or current, and we measure the second parameter. So if we apply amplitude perturbation of potential, we measure perturbation of current, and vice versa. And when we divide one by another, we get impedance. Okay. So I'm going to talk mainly about impedance of polymer electrolyte fuel cells. And here you could see a typical spectrum. So when you plot the real part of impedance and imaginary part, this is called Nyquist spectrum, and you get these two semicircles, two arcs, which are shown on the left, and the rightmost arc is usually due to oxygen transport in the PEM fuel cell channel, and the left arc is most interesting because in this arc is everything else, which is of tremendous interest for PEM fuel cell designers. So it's an oxygen transport in the catalyst layer, oxygen transport in the gas diffusion layer, it's proton transport in the catalyst layer, and this is oxygen reduction reaction, Faradaic reaction or charge transfer reaction. So everything is in this leftmost arc, okay? So the problem of theory is to extract parameters from this spectra, okay? This is a task for the modelers, if you wish, to understand the spectra, to extract transport and kinetic parameters from these curves. Okay, so on the right side, you see it's just a high frequency part, and you could see that there is no, okay, I will talk about it later. So there are two approaches to understand the spectra. The most popular and which has sort of 100 years old is equivalent circuit approach. So what people do, they measure the spectrum. In this particular case, this is a spectrum of pseudo-catalyst layer clapped between two membranes. This is just a way to measure the transport parameters of catalyst layer in a fuel cell. Okay, they measure spectrum and then they arrange some equivalent circuit, and they feed this impedance of this circuit to the experimental points, and then they say, okay, now we know these parameters of this equivalent circuit, and we can say that this parameter describes protonic resistivity, and this parameter describes electronic resistivity, things like that. This approach is very simple, but not reliable, actually. It has been strongly criticized by classics in the field, and because any equivalent circuit is not unique. You can always construct another circuit which would give you the same curve, and you are not sure if you are on the right side or you are wrong, okay? So of course, physics-based models are very much more interested, much more important, and there is a tremendous interest in these models, okay? So after this short introduction, I'm coming to outline of my talk. So I'm going to present you transient performance model of the cathode, of PEM fuel cell cathode, which is source of the largest source of potential losses in the fuel cell. And then I'll show you what parameters we could extract from impedance spectra. And then there is a very big interest in low platinum fuel cells nowadays. So everybody wants to make efficient fuel cell with platinum loading 3 to 4 times lower than typical platinum loading, as I would say, okay? Then there is a very interesting technique which is called distribution of relaxation times. I think I would hardly have time to show you catalyst layer with poor electron conductivity, but it's not really very important. So let me go further, and then we'll come to conclusions. Yeah. So motivation is, of course, to make impedance models for real operating conditions, real operating regime of fuel cell, and generally at high currents, unfortunately, analytical models do not work, and so your model should be numerical, unfortunately. But for low currents, we can go with analytical solutions. And the model should have ideally no empirical elements, okay? So the core of impedance models I'm going to show you is a transient model for cathode layer performance, okay? This is a very well-established field which has a long history, and a lot of people made contributions to this field. So some milestones are listed here in the bottom of the slide. What you see is actually the slab. So this is a catalyst layer between electrolyte membrane, which is on the left, and gas diffusion layer. And here we have oxygen concentration, which decays, which comes from the left. Oxygen comes from the left side, and it decays towards membrane. And we have proton current, which comes from the other side, from electrolyte, and it decays in this direction, okay? And we have oxygen reduction reaction over potential, eta, which is of particular interest because this parameter governs the rate of oxygen reduction reaction. Okay, so we need some equations for these three parameters, but that's not all. In fact, in the fuel cell, we have also oxygen transport in the gas diffusion layer, which we also need to take into account. And we have a oxygen transport in the channel, which is also very interesting, actually, process, which also contributes to impedance. So basically, what we want to have a model which would take into account all these transport processes if we want to describe a real operating fuel cell, okay? So I'm not going to press you with a lot of math. Just let me show you the basic equations which stand behind the model I'm going to discuss. So in the catalyst layer, we have the first equation here. Can you see my pointer?
Yes, we can see it.
Okay, good. So in the catalyst layer, we have charge. This is a proton charge conservation equation, which is a second order equation for overpotential. It includes proton conductivity and the term due to double layer charging. And the right side is the Tafel rate of oxygen reduction reaction with oxygen concentration here. And this is exchange current density. Okay, we have oxygen transport, which is just a standard diffusion equation. Again, on the right side, we have a Tafel rate of oxygen consumption in the catalyst layer. Okay, this is a key system. And that's not all, because we have transport of oxygen. We must transport oxygen through the gas diffusion layer. It's simple linear equation, which is shown here. Okay, we have some interface conditions, which are continuity of fluxes and concentrations, of course. And in the channel, which we have just a simplest approximation. This is a so-called plug flow approximation. So the flow is constant velocity v, and the oxygen is transported along the channel coordinate z. And on the right side, we have sink of oxygen in perpendicular direction. So this is a flux of oxygen in the GDL, in the gas diffusion layer, in the direction perpendicular to the channel, okay? This is standard so-called 1D plus 1D approach, which is extremely useful, very useful, because in some cases you can even get analytical solutions of this system, okay? So basically what you could do then with this system, as you could see, it's strongly nonlinear due to these exponents in a catalyst layer. So you could linearize it and Fourier transform. And then you apply small amplitude perturbation of concentration over potential and what else? Yeah, all concentrations in the catalyst layer, in the channel, everywhere, okay? And over potential. That's, we have two parameters now. Fine. And then you get a system of linear equations for the perturbation amplitudes. I won't discuss it. You could find details in papers. Papers are listed in slides here. So if you are interested, you could just look. This is just a technique, mathematical technique. There's nothing special about it. It's just a standard procedure of linearization and Fourier transform. And then you get impedance. So, but, yeah. So actually experiment which has been performed, which I showed you on the next slide, was performed with a segmented cell, okay, segmented cell. So a colleague of mine, Tatiana Reshetenko, measured impedance from the cell with segmented electrodes. And consequently, in a model, we have actually divided cell into 10 segments, as you could see on the right side. So this curve on top is a concentration of oxygen in the channel, which provides a sort of boundary condition for this transport, through plane transport in individual segments, okay? And this is actually a tricky thing. Okay, segments are, as you could see, impedance of every segment, they are connected in parallel. So we calculate total impedance of the whole cell according to this equation. It's just a parallel connection of individual impedances from segments, okay? The trick is thing that flow in the channel transport perturbation of oxygen concentration from one segment to another. So segments are not isolated, okay? The segment which is located downstream knows what is going on in segments which are located upstream because the flow transports this information. So the whole thing is really tricky and very interesting, okay? And this is experimental setup which Tatiana Reshetenko has built at the University of Hawaii. And what you see on this is a segmented cell with 10 segments, and this is direction of oxygen flow. And she could measure impedance from the whole cell and from each individual segment simultaneously, okay? So we actually applied our model several years ago to, we fitted our model. This is a plot I showed you, but it is actually the left red curve is, we ignored at the first approximation, we just ignored the right, this low frequency arc, and we fitted just these points. So we fitted our model, assuming that stoichiometry is large, there is no contribution from the channel, we cut it, we just sort of discarded it, okay? Well, we got quite good set of parameters. So TIFL slope is 30 millivolt, which is typical for this type of fuel cell. Proton conductivity of 20 millisiemens. This was a bit too high. I would discuss it in a minute. This is volumetric AA capacitance. So it's normal. Again, it's very normal. What was strange and unusual is pretty low value of diffusion coefficient in the catalyst layer. This one, 4 times 10 to the minus 5th centimeters squared per second. But this parameter is a kind of effective parameter which includes many interesting details I'm going to show you later. So, and this is a diffusion coefficient of oxygen in the catalyst layer, or in the gas diffusion layer, sorry, which is actually also quite reasonable, okay? So what bothers us most is that here we expected straight line. You see the red curve in this circle, it shows a straight line. This straight line is a characteristic of proton transport in the catalyst layer. And theory gives a straight line with a slope of 45 degrees in these coordinates. But in reality, you see the fuel cell shows much higher slope here. So the impedance goes much higher, with much higher slope. So we start looking at literature and found 2 papers, quite respectable authors. They explain this effect by non-uniform proton conductivity through the catalyst layer. So they said, okay, catalyst layer conductivity is higher at the membrane side and is low at the GDL side. Okay, we tried to model this effect. We inserted parameter S, which is a shaping function, and we took exponential shape of proton conductivity through the depths of catalyst layer. So in the case, this is exponential shape, as you could. If beta is 0, you get the uniform shape, which is also nice. So if frequency is large, you can solve this equation analytically. You get impedance, just to show you that solution is there. So impedance can be expressed through the Bessel functions. And we fitted this impedance to measured spectra, measured by Tatiana and her setup. And now you see this is 45 degrees line. Points are experiment, and red line again is a fitted model. As you could see, model nicely fits the curve, the experimental curve now. And okay, we could be happy with that, but the shape that we got from this shape of conductivity was really very, very strange. We have at the left side, at the membrane side, proton conductivity almost as high as a bulk conductivity in NAFION, in bulk NAFION. And on the left side, we have vanishingly small conductivity, which is really, really hard to believe. Although average value was pretty good, in agreement with data from other authors, okay? We started thinking that maybe this is not actually the correct explanation. We started thinking about another explanations, and we came up with the idea that there might be some capacitance in the catalyst layer, which we do not take into account, did not take into account. And if this capacitance is there, then the slope of the Nyquist curve would be really high. This is shown here. So on top, you see the exact solution of our model for high frequencies, and it describes straight line with a 45 degrees, as you could see on the right side. If we add this capacitance, as shown here, to the catalyst layer, to this impedance, okay, we get higher slope. So we just not discussing about origin of this capacitance. We just inserted it into our model. We inserted it into segments in parallel to impedance from each segment, and we calculated, fitted again cell impedance. Both models with non-uniform conductivity and with this, we call it external capacitance, nicely fit the curve at high frequencies, which you could see on the right side. This is high frequency panels. This is model with non-uniform conductivity, 45 degrees line, but we have a higher slope, as I said. This model, and this model also even better fit, okay? But parameters which we get are quite different, especially proton conductivity. In this case, is a model with external capacitance. Conductivity is an order of magnitude lower, which is much more realistic, I would say. So now we have a very big experience with fitting these experimental curves from different cells. And I would say that real conductivity lies in the range of 1 to 10 millisiemens per centimeter, millisiemens. So it's really very low, typically, unfortunately, I don't know why, but it's really very low, and sometimes it could be even lower. In the best samples, what we had, the conductivity reaches value of 10 to 20 millisiemens, but not higher. Okay, so what could be the reason of this external capacitance? We don't know, but we can only guess that actually there are some papers which tell that water in a catalyst layer is a weak electrolyte due to impurities. And if it is, then we may have a system of double layers inside the catalyst layer. So we can have water, and we have water, which is electrolyte. We have NAFION, which is also electrolyte. At the interface, we would have two double layers because these are two electrolytes with different concentrations, okay? And we have water on carbon also another double layer. So might be, we just presume that this system is connected in parallel, and we may have capacitance due to this story, okay? So my next story would be about effect of NAFION film in low platinum cells. So low platinum cells are of really tremendous interest, as I said, and some 12 years ago, I would say, or 10 to 12 years ago, people tried to reduce a platinum loading by a factor of 3 to 4. So what you see on the left side is polarization curves of the cell produced in Nissan company. So this is cell 0.35 milligram platinum per square centimeter is 0.12. And you see in the current, in the range of current below 1 ampere per square centimeter, everything is fine. So the decay of this curve is as expected because you have lower loading, because you have lower electrochemical surface active area. And so because of that, this curve goes in parallel practically to the high platinum curve. But above 1, something strange happens. This curve starts to decline faster. And this is the people call this overlinear transport loss, which is unexpected. Something in the cell, in the low platinum cell, contributes to generate this excess power, excess voltage loss, I would say, okay? So on the right side, you see there's just a cartoon. So this is an agglomerate of carbon particles with platinum on external surface. This is typical materials used in PEM cell catalyst layers, and they are usually pictures show that these agglomerates are surrounded by NAFION film. So oxygen must be transported through this film to reach the catalyst layer. Okay, and actually it was. There is a kind of agreement in society, in communities, that this transport of oxygen through this film is responsible for this overlinear transport. So to model that stuff, yeah, there are a lot of experiments on measuring oxygen transport resistivity of the film. And let's have a look at this curve on the right side. This is platinum loading. As you could see, when you decrease loading, this resistance is tremendously growing, you know. So by maybe 2 orders of magnitude almost. Okay, so that's the origin of this overlinear transport. To model that stuff, we just designed a very simple model. I would say in the spirit of model which Karen developed with Michael Eickerling several years ago. So this is a single pore model of our catalyst layer. So we have a single pore, and we have a platinum on carbon layer, and NAFION film in between. So we want just to explicitly incorporate NAFION film into our model to understand how this transport affects this cell impedance. Okay, so again we write equations. It's oxygen diffusion along the pore, oxygen diffusion in a radial direction through the NAFION film, and oxygen reduction reaction on this interface between NAFION film and platinum carbon layer, and again TOEFL equation for this rate. So and we couple transport equation along the pore and in radial direction in a 1D plus 1D manner, quite similar to what I show you in the beginning of my talk. Okay, so this is just a standard trick. Okay, so the first thing you could do, you could solve. Again, I won't show you equations. It's just a matter of techniques. You could find them on the paper, but first thing you could do, you could just find static solution. And it appears that in this system, there is another limiting current density. And this limiting current density is due to oxygen transport through the NAFION film. Okay, so an interesting thing that this limiting current density is proportional to thickness of catalyst layer. And we know, and everybody knows, that catalyst layer, low platinum catalyst layer are just 3 to 4 times thinner than high platinum. So what they do, they just reduce thickness. The structure of the system is the same, but the thickness is 3 to 4 times lower. And because of that, in a high platinum cell, you don't feel this limiting current. In a low platinum cell, this current immediately comes into play and limits performance, limits your polarization curve. It's a kind of in terms of our model, explanation is very simple. In this system, you have your oxygen flux is distributed over the length L, T, and in this system, the same flux, if you want to get the same current density, is distributed along the thickness, which is three times low. Of course, you have current limitation. You start feeling this. Okay, so we just now we switch to impedance. We inserted this model into our model for segmented cell, and we calculated impedance and fitted the curves. These are fitting assuming that we have this external capacitance. So two, again, blue points are experiment, red circles are our fitted model. And in the high frequency region, we are pretty good. And in the middle, at high currents, we are not very good. We have some strange stuff here in the low frequency domain, but we were not very much care about it because NAFION film shows up at high frequencies, fortunately. Okay, and so we got what we got from this fitting. We got oxygen diffusion coefficient in the NAFION film, which is a red line. Which is a blue line shown here. We have NAFION film transport resistance, which is of most importance, most interesting for community. And this parameter, it jumps in the low frequency region. We presume this is because we do not measure it carefully because it doesn't, contribution of this transport is too small. Impedance is not able to capture it correctly. But in the high frequency region above 300 milliamps per square centimeter, we have variation between 0.5 and 0.2 seconds per meter or whatever. This is strange units, but this is nicely agrees with the data published in literature. Okay, so furthermore, most recently we just applied, we did the same trick with local. So what I showed you before was a whole cell impedance. Now we did the same trick with local impedance. We fitted every single local impedance with our model, with our local model. And moreover, we assume that we have not a single pore, but we have a system of pores. So pore size distribution was taken into account. So this is a real pore size distribution with a blue curve measured by porosimetry. And we just approximated it by this red stepwise function. And we got, I'm sorry. So these are fitted local spectra, and what we got is shown here. We fixed film thickness at 10 nanometers to get more reliable results, which is, this parameter is quite well known from literature, and we got a resistivity of 0.4, which nicely agrees with other data. Okay, so I think that again, impedance is much faster and much simpler than all the methods used by other authors in this field. So we think this really could be a very, very interesting, very attractive technique to measure and to study properties of this NAFION film in real operating cells. Okay, and the last story I'm going to show you would be about distribution of relaxation times. This is very interesting, very nice technology. So what is it about? So what you could do? What this on the left side, you see typical PEM fuel cell spectrum, okay? Roughly. So you could say, okay, I will approximate the spectrum as by RC circuit, by parallel RC circuit, okay? So this is shown here. So this is RC circuit impedance plus high frequency resistance, which is shift of this arc from 0 point. This is contribution of membrane, typically of bulk membrane. So I will just can write this and say, okay, I'm happy with it, but in fact you would not be happy because the fitting would be very good, very bad, sorry. Much better result you would get if you denote RC as tau, multiply by some function of tau and integrate over all tau. What does it mean? It means that you seek impedance as a sum of RC circuits, infinite sum of RC circuits with different characteristic times. So this function gamma is called distribution of relaxation times. This function is very interesting. I will show you in a second. So from this derivation, from this simple consideration, it's obvious that a gamma, if you have a really single RC circuit impedance Z, then gamma would be a direct delta function. Okay, if you just cut a single frequency from the spectrum. Okay, in the general case, however, finding gamma is not a trivial task because this is Fredholm equation of the first kind, which is ill-posed problem. So what does it mean? So ill-posed problem means that if you approximate integral by some formula, some numerical formula, you would get matrix A, which is very bad. This matrix has a huge spectral radius. If you try to solve this equation directly, you will get absolutely crazy jumping solution, which has no physical meaning. Some 50 years ago, Andrei Tikhonov, a professor from Moscow State University, developed a famous regularization technique for solution of these ill-posed problems. Actually, you multiply by A transposed on the left this equation, and what you do, what is a crucial step, you add here. This is called regularization parameter, and I is a unit matrix. So Tikhonov said, I will spoil a little bit my matrix, but make the whole problem well posed, okay? If you add, you improve quality of this matrix tremendously, okay? So selection of gamma is a non-trivial task. I won't discuss it because it's sort of beyond my talk. So, but the method is really works nicely. It is widely used in many fields. For example, when you go to a dentist and she or she makes a 3D picture of your jaw, the Tikhonov method is working in computer. So, but unfortunately for fuel cell spectra, this method is not sufficient. It works, but not perfectly. And the reason is we want to find, the reason is that individual processes, transfer processes in fuel cell might be close to to parallel RC circuit, okay, impedance of it. That means that we want to find function which is close to delta function, which has tremendous, huge gradients, okay? And pure Tikhonov gives oscillation. So this is what you see. This is solution of numerical Fredholm equation, DRT equation, red line. And you see it gives correct position of RC, solution for the single RC, parallel RC circuit. It gives correct position of this peak, but unfortunately it's negative non-physical oscillations. So actually there are a lot of techniques how to overcome this. Actually, I also tried to apply some technique which is called projected gradient technique. It works. Here you see how this technique works. So this is two RC circuits connected in series. So two peaks, okay? So this is an imaginary part of impedance, and this is a DRT calculated from Dirac-Tikhonov, and this is DRT calculated from Tikhonov plus projected gradient. So we have no negative oscillations anymore. And what we get, I want to stress that from DRT we have two things. We have position of our process on the frequency scale, which is very important. This is characteristic frequency of our process. And the second thing, if we integrate this peak along tau, which is parameter which is inverse to frequency, we get partial resistivity, contribution of this process to this R, which is shown here. Okay, again, this is extremely important. So look, we know nothing. We just measure impedance. We solve some mathematical problem, and we get a lot of information about fuel cell. In principle, we may get parameters. We get frequencies. We get partial resistivities. Of course, you have to identify peaks. That's really important. So the code which is for solution of this problem is, you can download it from GitHub. The link is here, and I will show you if you are, those who are interested could try. If you are familiar with Python, you just can try and test this code. So this is I'm close to. Okay, so I need a couple of minutes. So that's what we did with we tried to we calculated DRT, having this technique, calculated DRT of low platinum PEM fuel cell, and these are DRT from different for several current density, 200, 400, and 800 milliamps per square centimeter. From again, these are local spectra. This is a real part of impedance which was used for calculation of DRT, and circles here is actually reconstructed real part from you, because you can solve the problem back. You use the experimental data, but then you can calculate integral and recalculate real part again. So as you could see, they just fit nicely. And this is our DRT. This is actually resonance frequencies I was talking in the beginning of my talk. You say these are just masses hanged on springs. So we have three processes. So the leftmost process is oxygen transport in the gas diffusion layer. This is oxygen reduction reaction plus NAFION transport in the film. Even DRT is not able to separate this. And this is oxygen transport in the void pore. We did a lot of work to identify these peaks. We just, plotted frequencies of these peaks versus segment number and resistivities. This is leftmost peak, which is oxygen transport in the GDL. You could see it decrease. So it looks like we have flooding towards the outlet, cell flooding, okay? Because resistivity grows and characteristic frequency decays, which means that, again, the diffusion coefficient decays, okay? And we managed to identify the NAFION film resistivity by comparison of this DRT with DRT of high platinum cell. Since I'm almost run out of time, I won't talk about it more. So if somebody is interested, just send me an email. I could give you more details on that. And so with this, I come to my conclusions. So real part of impedance is really a challenge. High frequency part, sorry, of impedance is a challenge. Some model for single agglomerate impedance with all double layers, with water, with NAFION, with water, which probably is electrolyte, is needed. And I think that DRT is our future. It tremendously simplifies measuring of partial resistivities, of individual processes. So you don't need any physical models. You just measure impedance and calculate DRT, that's it. Okay, it is hard to separate Faradaic and NAFION film resistance. So far, we did not manage to do that, but we are working on that, okay? And there is a lot of things beyond this talk, like there is a very interesting emerging field of concentration impedance spectroscopy and also nonlinear electrochemical impedance. This is also very, very interesting, very powerful technique. And generally, I have to say that the power of spectroscopy, impedance spectroscopy is tremendous, and we may expect further growth of this field. Thank you very much for your kind attention.
All right. Thank you so much, Andrei, for that talk. And so now I think we can go to questions. Are there any questions?
Sure.
I think you can unmute yourself.
Yeah.
If you do. Maybe I can start with a question. So this
Yeah.
interesting external capacitance,
Yeah.
right? The water catalyst and the water NAFION. So in my mind, are they always parallel to each other? Because don't you, because I was trying to reconcile that with your film idea as well, right?
No, you're right. You're right. The capacitance of carbon and NAFION and platinum NAFION, it's practically the same. But carbon water is something different, I think, you know.
Okay, because it's not got as concentrated an electrolyte.
Yeah, it's another electrolyte. Maybe. There are some indications that water is electrolyte due to impurities. So you may have some capacitance in this double layer, which is dark yellow. Okay, here.
Okay.
Yeah.
Okay.
And of course, you have two capacitances here between water and NAFION. If we really believe that water is a electrolyte, then you have a mix, two immiscible electrolytes, and there are two double layers at the interface.
Mm-hmm.
That's what we think might be the explanation. Because you know, as soon as we insert this capacitance, we get really very nice fitting, and we get very, very reasonable values of proton conductivity. So we believe there is something, really something inside the cell, some capacitance which has not been taken into account before.
Mm-hmm.
Okay.
Okay, interesting.
Yeah.
Let's see. Yeah. Well, another question would be, so you said that the 30 millivolts per decade Tafel slope was typical. What's the origin of that, right?
This is first of all, this is per exponential basis. If you calculate for electrochemists, it's more they usually express it per decade, you know. So you have to calculate by 2.3, then you have 70. If 70 millivolts per decade, this is a number which you could find in many papers. They just measure it. The source, I don't know. There is some rate determining step in the oxygen reduction reaction. Some rate determining step has this potential.
Okay.
That's what I think. Yeah.
Okay, so you think it comes from some intrinsic kinetics?
Yes.
So then it's a further step in the mechanism then.
Yes. I'm pretty sure it is. Yeah.
Well, maybe another question would be how. So your models for the catalyst layer are one-dimensional in general, right? Well, with the exception of the film. Oh yeah, so you have this. So
it's not one-dimensional. I would say it's quasi two-dimensional because we have transport along the pole and we have transport in radial direction. Everything is there. So. Yeah.
So do you account for the double layers in the radial direction? Yeah.
No, there are no explicit, like in your work. Of course, you did it because this is essential. We don't describe double layer explicitly. We just say there is something at this interface which gives us Butler-Volmer rate or Tafel rate of oxygen reduction. So we do not explicitly solve for double layer structure or things like that. No, it's just a kind of effective approach. Again, if you wish to model big practical system, you just cannot get into these small details. This is what I think.
Yeah. Okay. Interesting.
Yeah.
Yeah. No, that's true. I mean, it's amazing you can get analytical expressions for this kind of system.
No, we were really astonishing that from this simple model we get correct thickness and resistivity of film. This is really amazing.
Yeah.
So impedance is very sensitive, very sensitive.
Okay, great. Nitish, did you want to, I don't know, like,
Yeah, I mean,
take care of the questions? Yeah, thanks.
yeah, sure. Yeah, there's one question from Sudarshan Vijay. Very interesting talk. If I understand correctly, you mentioned in slide 11 that there are some analytical solutions possible for situations.
Yeah.
Are they available? Are there any available for high currents?
No, for high current, we don't have analytical solutions. You know what we usually assume in analytical solutions. I'll show you on this slide. We usually assume either eta is constant, almost constant, of course. It's not constant, but eta is a variation of eta through the depth is small. This is a case of fast proton transport, okay, through the catalyst layer. This simplifies greatly the system of equations, and you can get analytical solutions. So this is a catalyst layer in which oxygen transport could be poor, but proton transport must be fast. Okay, the other case, you can assume the other way around. You can say, okay, oxygen transport is fast, but proton transport is poor. So this curve C, this black curve, is practically constant through the depths, but this curve is taken into account accurately. So in these two cases, you could solve the system. Yeah. Even in these cases, the solution are very bulky, I would say, you know. So if you are in a high current region, both these curves cannot be assumed constant. They could be quite sort of gradients could be pretty high, and you have to solve the system numerically, unfortunately. Yeah. Mm-hmm. So that's our experience. Mm-hmm. Okay. What I mean by low currents is current, let's say, below 100 milliamps per square centimeter for typical mm-hmm. set of fuel cell parameters. Mm-hmm. Yeah. Okay. Yeah.
I'm also curious if you have applied this model to study other kinds of fuel cells or other like general electrochemical reactions.
It is a very general model. I think it can be applied for solid oxide fuel cells mm-hmm. and maybe for direct methanol fuel cells. I didn't do that because I was focused mainly on PEM mm-hmm. because of Tatiana. She's doing experiments mainly with PEM, okay? But yeah. Basically, this is a very general model. Just some minor corrections are necessary to switch to, for example, solid oxide fuel cells. Mm-hmm. Just minor corrections, yeah. Mm-hmm.
Yeah, I think maybe we can take inspiration for this for now we're considering full electrolyzers. So yes, this is great. Mm-hmm. Yeah. Any other questions? Okay, great. If not, then thank you so much, Andrei, for that talk again.
Thank you very much. So I'll send you a PDF if somebody is interested, and maybe some further questions. If people have some questions, just drop me an email. Yeah.
Okay, great. Well, we'll upload it. We'll upload it to YouTube and send you the link.
Okay.
Yeah. Okay. So sure, I think then they can have your explanations with the slides.
Yeah. Thank you. Very good.
Okay.
Thank you.
Great. Yeah. All right. Mm-hmm. Thank you. So take care.
Yeah.
Hope to see you.
Thank you. Yeah, bye.
Okay. Thank you. Bye. Thank you. Bye.